Thank you for coming back. Last time we went through some basics of quantum field theory. And this time we are going to say something non-trivial about CFTs and VOAs. In particular, we are going to use stable homotopy theory to learn something non-trivial about VOAs and CFTs. So this, at this stage, might sound a little bit too fancy, since last time we were talking about, quantum field theory in 0 and 1 dimensions. So you may not know exactly what is stable homotopy theory, but you should have the impression that it's about spaces. So what are spaces that we should be looking for if we are interested in VOAs or CFTs? Well, we can certainly try to look at the space of VOAs or CFTs. So I think anyone in the audience should have a better idea of what this space looks like. But for me, when I learn about CFTs, I first encounter a sequence of discrete points, maybe given by minimal models. And some of these points have names attached to them, like IC model and so on and so forth. And then I encounter another sequence of points given by, let's say, WW model, and then a bunch of other things. There might be some continuous families parameterized by one parameter or two, but I'm less familiar with those CFTs. Okay, but if you look at this, this is not a
modular space of full CFT.
Yeah, you can consider this as a modular space of full CFTs, but I have to draw it in a way that is will be abstract. You can also view this as a space of VOAs. Right. So if you want to study homotopy theory of this space, it's going to be not very interesting, right? Well, because discrete set of points carry no interesting topology. So what should we do? Well, to turn this into something that is more interesting is try to fill the space between discrete points. This can be done naturally by not just looking at CFTs, but QFTs in general. And this is what we will do today. So we are going to look at space of QFTs, but we are still going to stay in 2 dimensions. So it will be 2-dimensional quantum field theories. And to have better control, we are going to consider 2D 1,0 quantum field theories. And that's indeed where we ended last time. So what do we know about 2D 0,1 QFTs? So in general, they are not conformal. So generic 2D 0,1 theory might live here. So you will not be one of the discrete sequence of dots. But then, as I mentioned last time, we expect that there is a certain action on the theory, and there is some trajectory given by this operation known as RG flow. And if we start with a good enough theory, we should end on a theory that is scale invariant. And in 2D, that means the theory should be conformal. So there should be trajectory from that theory to conformal field theory. So what do we know about general, the space of general 0,1 theories? Well, in general, it's hard to make any concrete statements. And for mathematicians, the first kind of questions that one should ask is, what is the homotopy groups of this space? So let me use T to denote this space of 2D 0,1 theory. And again, it seems that we know very little about it, except that physicists has tried to understand invariance of quantum field theories. we have encountered invariants of one-dimensional supersymmetric quantum mechanics, namely the Witten index. And can we consider some invariants also in this world to learn about topology of this space? So what are invariants in this language? They are functions on pi 0 of this space. So invariants can be valued in C, Q, Z, or more fancy, let's say a billion groups, right? And then we can use that to learn a little bit about what this space of components looks like. So any question at this stage before I introduce very basic invariants of 2D 0,1 theory? So invariance number 1, we know that very basic way to characterize a VOA or a CFT is by its central charge. So here in the world of 2D 0,1 theory, there is an invariant that is playing a similar role. I will refer to it as the gravitational anomaly. What is this invariant? So recall that if I start with a physical theory and then flow to infrared fixed point, so what do we know? We expect that it's a fully fledged physical component field theory. That means that there is going to be left moving modes, so right moving modes. And then the space of state should form a representation of both the left moving and the right moving VOAs. So they can have different central charges, CL and CR. But it turns out that only the difference of them is a good invariant. So the gravitational anomaly for VOA is simply 2 times the right moving minus the left moving central charge. So there's a way of characterizing this without referring to the CFT fixed point. So the right way to talk about it is by first realizing that in general, when we talk about a 2D 0,1 theory, it's actually not a theory by itself. So it actually lives on the boundary of bulk theory. The picture that maybe you have encountered many times in the context of rational CFTs. But in this case, this 3D theory is not a complicated TQFT. Instead, it's assumed to be an invertible theory. Basically, this means that it's quite boring. The Hilbert space on any Riemann surface is one-dimensional. And then to fully characterize this, we only need to know the partition function on a closed 3 manifold. And in this case, it's given by considering 4 manifolds whose boundary is a 3 manifold. And then consider the value of minus P1 over 48 times D. So another way of saying this is that this is a gravitational transaction theory at level. But anyway, this is a good invariance of 2D 0,1 theory. So if you do not like this picture, you can simply remember that it's the difference of left moving and right moving central charges. That should be good enough for our purpose. Because this is invariant, then we know that we can decompose T into subspaces with different gravitational. And then you can ask whether this space with fixed gravitational anomaly, are they going to be connected? Whether this D is just the ultimate invariant for 2D 0,1 theory. The answer in general is no, because there are different invariants. So the second invariant that I'm going to introduce is known as the elliptic genus. And this is, in fact, what I have already introduced last time, but we're going to do it again in a slightly different way. So now we want to define it as the partition function of the theory, just T2. Because this theory has fermions, I again need to specify the spin structure. Last time, when we have a circle, I mentioned that there are two spin structures. One is this periodic spin structure, another one is anti-periodic. And periodic means that it's non-bounding. Anti-periodic means that it's bounding. So here we are going to choose a spin structure that is periodic in both directions. And as a consequence, this is also a non-bounding spin structure. And this is actually a generator of a spin cobordism group in two dimensions. So very concretely, this means that if I have a fermion, and then I go around any cycle on this T2, I'm going to apply periodic boundary condition. This is a partition function, and if you believe in axioms of QFTs, you are always allowed to talk about such a partition function, right? And what would this depend on? So this should be a function of the parameters for this torus. So one can parameterize this torus by complex parameter tau bar, and then the area. So in principle, it would depend on these three parameters, so three real parameters, or equivalently one complex, one real. But interestingly, for good enough theories, it turns out that if you look at the tau bar dependence, or if you look at the dependence on the total area, this is going to be 0. So therefore, it only depends on tau. Equivalently, we can use the Q parameter, which is e to 2 pi I tau, to characterize it. So this is one way of talking about the elliptic genus.
Oh, I'm sorry, I think I missed something. So is your QFT the space of QFTs, CFTs, or is it QFTs?
Of QFTs.
It's all QFTs.
Yes.
So then what does it mean central charge for a QFT?
So here, this is a definition that only works for CFTs.
Okay.
Right. So for QFTs, one should really use this picture. And then the statement is that under RG flow, this theory in the bulk will not change. It's characterized by some integer, and that stays the same along the RG flow. So any other question?
This asymmetry that depends on tau but not tau bar is because it's 0, 1.
Yeah, that's exactly right. So yeah, since you ask, let me maybe insert a comment here. So there are different ways of looking at this particular quantity. So this is one. There's the one that I mentioned last time. So let's provide another. So if you really look at the picture where you have S1 and evolve it to get a T2. So you would conclude that this is again trace of over the Hilbert space associated with S1. And then you insert again -1 to the F, similar to the Witten index that we talked about. And then Q to L0, Q bar to L0 bar. So here, L0 is just H plus P, and L0 bar is H minus P. So what's happening here is that, again, because we have supersymmetry, and this is actually square of our Q, we will not have dependence actually on Q bar. Similar to the case of Winter index, we have a parameter that's the size of the circle, but the Winter index will not depend on it. So the story here is completely similar. So for any states with non-zero value of L0 bar, they're not going to contribute because the boson fermions are going to cancel. So that's another way to see that this only depends on Q. So any other questions about this?
Is the lack of A dependence somehow related to conformal?
Actually, no. So if it's conformal, then it's kind of obvious that this should be independent of A. But for general 0,1 theory, one can just compute this and then realize that this is expectation value of Q exact operator. And then there's a supersymmetry argument telling you that any operator of this kind, if you compute its 1-point function, it's going to be 0. Yeah, so here we're actually not using conformal symmetry. So any other questions?
I know the units for manifold, but what is the interesting?
Yeah, we are going to talk about it later. So here, this is elliptic genus of quantum field theories. And then there's also a notion of elliptic genus for manifolds. The relation between these two are like Winter index for quantum field theory and Euler characteristic of manifolds. So we are going to say more about it. So any other? Okay, so this is elliptic genus. So if I actually define it in this way, it will not be an integral series of Q. So you will involve some fractional power of Q. And this actually can be predicted by looking at how this 3D TQFT behave. So in particular, we would know how this transform under SNT transformation. So under T, this D elliptic will pick up a phase 2 pi I D over 24. And under S, it will pick up a phase that is given by e to 2 pi I, I think minus d over 8. And you can verify that this is indeed one-dimensional. Oh, I'm missing, I think I will put the minus sign here. It's indeed a one-dimensional representation of SL to Z. And that's the mapping class group action obtained from this 3D invertible theory. Right, so in principle, this is yet another way of defining this 3D theory, mod 24.
And this trace will be a modular form for that modulator?
That's exactly right. So, and that's what I'm trying to say next. So here, because of this rule, we know that this will involve some fractional power of Q. And for many people, we prefer integral Q series. And what can be done is the following. We just define another quantity that is the delicate eta function to the D's power times the elliptic. This quantity is sometimes referred to as the Witten genus. And this will actually be modular form of weight d over 2. So to be more precise, this is going to be in the ring of weakly homomorphic integral modular forms. And what is this? So, well, let me just do this. So this is ring generated over Z by the first two Iceland series, the modular discriminant and its inverse. So this is a very concrete ring that you can work with. So here, the normalization is such that C4. This is simply the data series for the E8 lattice. So you start with 1, and then 240, 2. 240 is the number of roots in of E8, and plus dot dot dot. That's 1 minus 504 q plus dot dot dot. So these are the first of the first two of the isotope series, and then delta is actually related to these two over rational numbers. So if you are working with rational numbers, there's no need for delta. But since we are working with integers, what happens is that if you take C4 cubed minus C6 squared, that's 1,728 times delta. So you should be able to divide by this number. So if we are working with integers, so you need delta as well, and then you also need the inverse of delta.
If we consider CFT with supersymmetry, what is this QFT genus?
So this is right. So if we are working with CFTs, we just use this definition, right? And then we know that it will now depends on Q bar, so we forget about it. And then so it will be counting this left moving degree of freedom coupled to right moving ground states. And if there's a unique right moving ground state, it will simply be the character of the left moving VOA.
So if we did an n = 1 minimal model, it would be 0 if the labels are odd and just one character if the labels are even.
Yeah, that's probably right. So if you only have right moving degree of freedom and it's supersymmetric, then this is going to be an integer. But if you normalize, it will be a modular form of non-trivial weight. So any other question about this simple ring or anything else? So this is invariant. Then one can ask, well, do we clearly know that this could have different kinetic components? Because there are usually more modular forms in a given degree, right? Usually infinitely many, because here I'm allowing to have negative power of Q. So usually you can have infinitely many obtained by, let's say, multiplying by the J function. Then there are two kind of questions that you can ask. The first type of question is that whether that's the end of the story, whether that's this invariant is strong enough so that you can distinguish every kinetic components. And the second kind of question is that whether you can get all the modular forms over here. So it turns out that the answer to both questions are negative. So this is not the ultimate, not a complete invariant. And also, we are not able to get every modular forms. So some modular forms just cannot be characters of VOAs. So how do we know this? There is conjecture. So based on earlier work of Siegel, and then by Soden technique. So their conjecture states that this space T is not just an ordinary arbitrary space. This, first of all, is a spectrum. And secondly, it's a spectrum for a particular generalized cohomology theory known as TMF. So this is a very complex statement, and we are going to decipher this. So here, spectrum is not in the sense of quantum mechanics that we have encountered before. it's in the sense of algebraic topology, in the sense of Brown's representability theorem. So recall that there's this famous Allenberg-MacLane spectrum given a abelian group. Then there is a sequence of spaces. They have the property that they represent cohomology in the sense that if I'm interested in getting this cohomology group in degree n with coefficient in A, then I look at homotopy class of maps from X to this space. So therefore, what this actually means is that if I'm interested in getting those abelian groups, so what this general cohomology theory, TMF, associate to a topological space, I just need to consider maps from X to the space of theories T. That's their conjecture. When I first learned about this sounds so unreasonable because it's so strong. So if you trust this, then you get a lot of prediction for 2D 0,1 theories. And it seems that these predictions can be easily falsified. So we look into this, work on this. We are not able to falsify any of the predictions. We're able to verify many of the predictions. So now I think it seems that this conjecture is simply true. But let's gradually and slowly decipher this further and talk about what's the concrete prediction that we get from this. So first of all, is there any question about this definition? Or sorry, the interpretation of this conjecture? So I haven't managed to tell you what is this general cohomology theory, but I will say a bit later. Okay, so why is this extremely strong? Well, if we take X to be a point, we already have a lot of non-trivial statements. So if I take X to be a point, on this side, this is TMF associated to a point. For general cohomology theory, this is often referred to as a ground ring, and it has a name. So I will often use pi star TMF to denote this ground ring. And we refer to this simply as the ring of topological modular form, for a reason that will be clear later. And then on this side, we are getting homotopy class of maps from a point to this space T, and that's exactly pi 0. What is this telling us? This is telling us that first of all, this is a complete invariance because this is isomorphism. And further, any topological modular form can be realized as a physical theory. So let's look at these predictions one by one. So prediction number one is that there are actually new invariants. So these are invariants of 2D 0,1 theories, and then they can be also viewed as invariants of VOAs that are beyond the usual characters. So how's this new invariance, pi star TMF, related to the old invariant? There's actually a map from pi star TMF to the ring of weakly homomorphic modular form. So the convention is such that here, this star degree is mapped to weight d over 2. So maybe I should clarify here that here there is a grading, and then that exactly corresponds to this gravitational anomaly. So if we are interested in this, let's say in degree minus d, then we should consider the d's the space of a field with gravitational number d. And similar here, if we are having a degree d topological modular form, under this map, it will be mapped to a weight d over 2 modular form. So, and this map is not injective. It has a lot of things in the kernel, and these are potentially new invariants. Fortunately, all of these are portion value, and a lot of them come from actually stable homotopy groups of spheres. So this is a general thing that happens for spectra. So for homotopy group of spectra, you always have such a map from stable homotopy group of spheres to this ground ring. So some of these portion value invariants are therefore image of this map, and we can characterize that in this way. So for example, what is pi 1 of S? So this is Z2, and this is generated by something that I will refer to as eta. And this people in homotopy theory sometimes refer to this as a Hopf invariance, because this is related to the Hopf figuration of the 3-sphere over the 2-sphere. So this, as maybe all of you know, that is Z. And then if you stabilize this, if you suspend this, you get mod 2 map here. So the generator here mapped to the generator of the Z2, and we'll denote that by eta. What is pi 2 of S? This is again Z2, and it's generated by eta squared. So this is actually a ring, so you can take eta times eta, and that turns out to be the generator here. What is pi 3 of S? This is actually Z24. The generator is often denoted by, this is another Hopf invariance associated with the Hopf figuration of the 7th sphere over the 4th sphere. So if you take the elements here that correspond to the Hopf figuration and then stabilize it, you get a generator here. So I can say a lot more about this new portion value invariance, but that actually will not be the focus of this lecture. I just want to mention a few to let you know that there are other invariants that are also modular beyond the characters. So one question for you is how to define this for VOAs. So this is an isomorphism. That means that for any TMF classes, for example, those classes listed here, we should be able to realize them by physical theory. So there is supposed to be some theory that realize this invariant, that invariant, and this invariant, and anything that you can write down, any class that exists in PyStar TMF. So for these invariants, actually we know how to construct non-conformal theory. So this is related to the sigma model that I mentioned in lower dimensions. So in lower dimensions, you can define, for example, this supersymmetric sigma model from given the input of a manifold. So now in 2D, one can also define sigma model given a manifold, but now there are going to be some requirement. So M has to be a string manifold, equipped with structure, also known as string structure. So I will not tell you what that actually means, but in low dimensions, there are many basic string manifolds. For example, S1, that's turned out to be a string manifold, and the choice of string structure is exactly a string structure. And the sigma model to that will realize this eta that I mentioned. Similarly for T2, that realize eta squared. And then for S3, that will realize nu. But then there are more interesting classes here and also here. So there are some basic questions that we are not able to understand, like what's the CFT realization of C4? So one question is that, so there's a way of realizing C4 as a sigma model to a string 8 manifold. But that's a non-CFT realization. It's a sigma model realization. One question is that can we realize this by computational field theory? Yeah, this is also a perfect time to mention to answer the question about elliptic genus. So if one define a sigma model in this way, and then we can talk about the elliptic genus of the theory T that that is this sigma model. And the statement is that this is exactly the elliptic genus of this string manifold M. So there is again this problem about this normalization. You should normalize it, and then on the other side, you should perhaps again call it a Witten genus of the string manifold. So that's another prediction, but that's again not going to be the focus of this lecture. So the focus is actually the following. So here, you mentioned that this map is not injective, that leads to new invariant. But this map is also not surjective. So you cannot get every modular form in the image. So I'm going to erase this, but just keep in mind that these are the generators.
By sigma model, do you get CFT or QFT?
So by sigma model, you in general get a quantum field theory.
So because the algebra for this theory, what kind of the CFT?
Yeah, so that's exactly the question. So if you follow the algebra flow to the infrared, then can you describe it in a CFT language? Actually, for those invariants, there are ways of realizing them in CFTs. So these are CFT realization of this invariant.
What is the higher path for this?
So those are realized by a certain system of free fermions, but with a particular choice of the supercharge. So I can say more about this if you are interested. Yeah, but for this guy, it's not clear either how to follow this to the infrared to describe it as CFT or find some other CFT that realize it. So any other questions?
Yeah.
Yes.
So maybe so it's the idea that should be some vertex algebra with greater dimension given by C4 over some power beta function.
Over some power.
I mean, so you're looking for a theory which gives this invariant, right? Does it correspond to graded dimension?
Graded dimension. So in general, it can be a CFT with both left and right moving degree of freedom, right? And then you made by graded dimension, you're just talking about this elliptic genus.
Just the chiral path. Yeah.
Oh yeah, right. So there, again, you are summing over left moving degree of freedom coupled to right moving vacuum. And if there's a unique one, indeed, it's just summation over of the left moving degree of freedoms. And then it's supposed to produce C4 over power of eta. And then after multiplying that power, you get this. Yeah. Any other question?
Are your QFTs unitary?
So here we are working with unitary theories, and that's exactly related to this question. So actually, we now know if we relax this, what happened to this space. So whether if we consider the space of non-unitary 3D 0,1 theories, whether that just retract to this space, or there can be some interesting thing going on. So yeah, I think that's a great question, but I will not be able to answer it now. Any other question? So prediction number 3 is that only some of modular forms can be realized as elliptic general. So we have some familiar modular forms. For example, C4. That's actually allowed. It's in the image, and that's why we asked this question. So how about C6? It turned out to be not allowed by itself, but you can have 2 times C6. So I can, instead of asking this question, I can instead ask question for 2 times C6. But I also don't know the answer. And that's further complicated by a minus sign in the Q expansion, if you remember. And why we have a 2? Why have a 2 here? But from the point of view of signal model, there is it's related to Rocking theorem, where in certain dimension, A hat has to be even. The A root genus of a spin manifold has to be even. But at the level of quantum field theory, there is a way of understanding it, but I will not say more about it. What's more interesting is delta. So delta is again not allowed, although it's a very natural and nice modular form. You have to have 24 times delta. And how about delta squared? Again, not allowed. You have to have 12 times delta squared. The general rule is that if you want a k times delta to the k to be in the image, you must have 24 divide ak times k. So delta will not be allowed because, well, if you take 1 as a coefficient, then 24 will not divide that. But then if you take 24 times this, then it's allowed. So you can check that. Using this rule, you can predict what's going to happen. So for delta cube, that's not allowed. But the coefficient has to be such that when it's multiplied by 3, it's divisible by 24. So the minimum thing is 8. 8 times delta cube, that's again allowed. So this continues. So this is a very concrete prediction. And we can try to test this. And then several things can happen, right? So we can try to first test whether this is indeed true. And then we can see whether these bounds are actually sharp by going through the theory that we know. If it's not sharp, maybe that tells us that there might be some work that we should do. And then if we manage to go through these steps, we can then maybe ask for what are applications of this. That this shed some light on something. Well, for example, for physicists, if you have this, you can ask whether this has anything to do with quantum gravity, black holes, and so on and so forth. So we will explore that later. So because the world of fully flat CFTs seems a bit difficult to work with, namely we have left moving and right moving paired up in some modular invariant way, we are just going to work with CFTs that only have left moving degree of freedom. So why is that okay? Well, this is because we're working with general 2D 0,1 theories. And this is indeed a very general class of theories, right? So what are 2D 0,1 theories? Any supersymmetric theories in 2D. Also, any higher dimensional supersymmetric theories. But since it's higher dimensional, probably you want to reduce that on some choice of manifolds. Manifold of dimension d minus 2. It can be a torus or something non-trivial. So you can get 2D 0,1 theory in this way. But most importantly, for us today, if we have a chiral CFT, meaning only left moving degree of freedom, that's also 2D 0,1 theory, because we just let the right moving supercharge to act trivially on everything. So since we are working with general theories, this is just a special class of theories. So, but what we do want to avoid is a picture that we have chiral theory coupled to a higher dimensional bulk. Coupled to a bulk that is, let's say, some complicated 3D QFT like transaminase theory. We just want this invertible theory. And a good class of such CFTs are CFTs with holomorphic CFTs. So that's what we are going to work. So we are going to work with holomorphic VOA slash CFT. So this basically means that we are having a VOA with a single irreducible module, the vacuum module, and technical requirement is that the central charge is also 24 times the integer. So I think there are different conventions. For some convention, it's allowed to be 8 times the integer, but for today, we are going to take 24 times the integer. And we are going to put it on the left. So D would equal to, again, 2 times CR minus C left, but then there's nothing on the right. So it's going to be minus 48 times N. That's the gravitational anomaly. And then what do we know about the elliptic genus? Now it's just the vacuum character, right? And then we know that it has to be modular function. So this is the polynomial in the J function. So here, J is C4 cubed over delta. Has this famous expansion, Q inverse plus 7 for 4 plus 1968884. Is that right? And K can go from 0 to some positive integer. So this is the elliptic genus of a holomorphic CFT. And then we want to get actually the written genus. We are going to multiply that by e to the d's power. And then what happens is that the leading term is d0 times delta to minus 2n. dot, dot, dot. Now, this term is dangerous because it may not be in the image. So there are going to be conditions on B0. So it can be written in different ways. For example, n times B0, that has to be divisible by 12. So what's the allowed minimum coefficient? So when n is congruent to plus minus 1 mod 12, then B0 has to be divisible by 12. So the minimum thing is 12. When n is congruent to plus minus 2, it has to be divisible by 6. When n is congruent to plus minus 3, now 4, 3. And when n is congruent to plus minus 5, this is again 12. And when n is congruent to 6, then it can be 2. So we just continue here. Then we can test what we know about homomorphic CFTs against this prediction and check whether it's satisfied, whether it's sharp, and then whether we can get some interesting predictions. So some nice constructions of homomorphic CFTs that follows. First of all, there's a large class of homomorphic CFTs given by even self-dual lattice. And we're going to assume that the dimension is going to be a multiple of 24. So for example, one can take the Leach lattice or some other lattice in 38 dimensions and so on and so forth. Then for those, unity genus is just going to be the theta function of this lattice. So what do we know about theta function of even self-dual lattice? A theorem by Borchardt states that actually 24 always divides B0, regardless of the value of n. So in other words, it's always this constraint is always satisfied if we work with just these homomorphic VOAs coming from even self-dual lattices. So another way of getting homomorphic CFTs is by first starting with some lattice and then consider orbit folding. Some lattice will have non-trivial automorphisms, and then there's a construction obtained by using this symmetry to get a different CFT known as orbit folding. And then, oh, sorry, what am I? Yeah, so let's wait a bit because let me just mention another construction. So this will be 3. Right. So for this, if we take actually n equals 1, what we know is that there's a complete classification of homomorphic CFTs with standard charge 24. That's Shellicon's list. And then if you go through all the theories on that list, what you'll find is that indeed 12 divides B0, which is exactly what we expect. So the constraint is satisfied and also is saturated in this case. Okay, so how about higher n? For those, you can use this orbifold construction. And then if you go through the literature, which we did 1 year ago, so I actually don't know whether there's any newer developments. For n equals 2, the observation is that all the theory that was that has been constructed so far satisfy again the condition that 12, divide B0. For n equals 3, you have 8, divide B0. So if you compare that with constraint, you realize that, well, those always satisfy the constraint, but those are not sharp. So maybe that's suggesting that there are some holomorphic theories with n equals to 2, meaning central charge 48, or n equals 3, that improve on these bounds. So one can ask, what are these minimal theories? Minimal in the sense of these constraints. So we expect from, yes.
So if you do an orthogonal construction, then it's not holomorphic anymore, right? You then again use the Lamarck extension in some other direction.
So you have to be careful with this construction, but there are ways to. So in general, it's not, but there are ways to get homomorphic theories.
You make again a simple curve extension in some other direction.
I believe that this is what they did, but I will not be surprised that they also look at other possibilities.
Does physics predict that there exist minimal theories?
Sorry, could you say again?
Does physicists predict that there are indeed exist minimalist theories?
Oh, right. So that's a comment that I'm going to make. So the prediction from this conjecture by Siegel, Salt, and Teichner is that there's always fully fledged CFT that realizes. And it's not exactly clear whether this there has to be such minimal theories in the world of homomorphic CFTs. So that's why this is interesting question, I guess. Maybe I should first ask whether they exist, and then ask what are those homomorphic theories. Yes.
Yeah, sorry. No, I just think people use orbifold in different senses. So when you said orbifold, I think you just mean invariance by some group. He means taking variance next to some simple current extension.
Yeah, I think that's what's happening. So so my collaborator, Yinshan Lin, I think he actually explored maybe other possible ways of constructing theories of n equals 2 and 3 that is slightly beyond this, but so far we're not able to improve or find minimal theories.
Among the things which satisfy the Riemann.
Among Shirkin's list, there are several theories that satisfy this. So there are theories with this constant being 12, and then also there are a couple of theories.
How does the moonshine for you? Moonshine?
Yeah, so for moonshine, yeah, yeah, I somehow have the impression that the moonshine module would saturate this constraint, but I'm actually very confused by looking at the counter term in the J function or anything. Yeah, so yeah, but on that list there are several theories, and I'm not quite sure whether moonshine module is one of them or not. Yes.
So is there a specific role being played by this normalization of the J function in this case?
By
Because
eta function?
Sorry?
So normalization by eta function?
No, so you could take J function instead of 744, you could take some other constant.
Oh, there's no difference. So as long as you achieve some normalization by something that's divisible by either 24 or 12.
Yeah.
So right. So if you choose a different normalization of the J function that is really bad, shifting this by 1, then the constraint will be quite complicated, right?
Yeah.
So, but if you want to keep the form of this constraint, you better normalize it in such a way that this itself is divisible by 12. Okay. Any other questions? So, so it seems that this constraint is satisfied. In some cases, it's not sharp. So let's try to learn about black holes using this. So conjecturally, there is a class of very interesting homomorphic CFTs known as extreme. So what's the meaning of this? This somehow is motivated by this ADS CFT correspondence. So somehow 2D CFT are supposed to be dual to some three-dimensional gravity, and then we can look at this and then say that it seems that there the excitation beyond vacuum is some black hole, and that's supposed to be heavy. So then the corresponding statement and our CFT is that there's no real solar primary up to wave n. So beyond the vacuum, we can look at the partition function. So because there are going to be no primaries, so the you have this kind of expression. So you have the action of the real solar generators L minus 2 and 3 on the vacuum. So this two, well, and then there can be corrections, but correction can only happen at order Q. So we can look at this, and then he realized that this is unique for each n. So, and if I take n equals to 1, that's the monster, and extrapolating from this data point, we can conjecture that they exist for every n, and they always have monster symmetry. Then later, for n equals to 2, it was realized by David Galto that if it exists, it cannot have monster symmetry. But David is still conjecture that it should exist.
I don't really understand what.
For n equals 2, if it exists, it cannot have monster symmetry.
But I thought you said it always has monster.
That's conjecture by Witten.
Yeah.
But then David is pointing out that it cannot be true already at n equals to 2.
And what is conjecture now? What should exist?
So there's no official conjecture after David's statement, but in the paper he mentioned or said informally that it's still expected to exist. Okay, so then one can check if this actually is compatible with the constraint. So then one realized that for n equals 2, it's actually already not compatible with the divisibility constraint. And the same goes for n equals to 3 and 4. So these are not allowed. So the next one, well, if I remember correctly, 5 is also not allowed. So, and then for n equals to, it's allowed again. Then the question here is that whether one can actually construct this and whether that have a monster symmetry or something else. So again, similar to this question, the prediction is that there is going to be some fully fledged CFT with both left and right moving degree of freedom, whose utility genus is giving this extremal partition function. But there's no guarantee that it can be realized by a homomorphic CFT. So the question is that whether it can be realized. So this is something that people in ADS CFT or quantum gravity would be interested in.
So do I remember back in the day, Matthias Gabriel gave a talk about this. He said that he had very strong, convincing, perhaps evidence that eventually, if it's sufficiently large, then these things could not exist. Do you know what the status of that is? I think it was like 40 or something. But,
I know some statement that is perhaps unrelated to that statement, but there are some ideas goes under the term swampland that leads to a prediction that none of them should exist, even for n equals to maybe for n equals to 6. Yeah, so it would be interesting to just understand this from the point of view of VOAs, like what's wrong with all of this. So far, it's just come out of this mysterious conjecture. But in the world of VOA, it's a concrete question. So they would not exist for some reason. And answering that in the world of VOA would teach us something about this conjecture. And so any other questions at this point? Yeah, I finally managed to find the short list of allowed n. So I don't know whether this would be useful, but n equals 1, that's a monster, 6, and the next one is 9, 13, 18, and so on and so forth. So it's not really periodic in any sense. So you expect that this is somewhat fractal.
What is that?
Hmm?
What is that?
What?
What is the numbers?
What are these numbers? These are just some special numbers. I can say this in a slightly different way. So the B0 is congruent to, are you asking for meaning of these numbers, or like what property they satisfy?
Why are you writing this now?
Right. So these are n's for which the extremal partition function can be realized by physical theories. According to the conjecture, they can be always realized, but not necessarily by holomorphic. Yeah, so if I include all theories, actually, there's a way of arguing that they can be realized by some complicated sigma model to some complicated string manifolds coupled to some other theory. So, but that's not terribly useful.
Question, please. So, in this extreme QFTs, you don't require supersymmetry?
So this is left moving. So they are also 0,1 theories in the sense that the right moving supercharge acts trivially. So this is a non-supersymmetric theory, but it's still supersymmetric in a boring way. That's actually fine. So yeah, so in a sense, the surprising thing is that one can make a non-trivial statement of purely bosonic VOAs using this conjecture that is in principle about supersymmetric theories. So I'm hesitating whether I should go to the next topic, but since there's only 4 minutes left, maybe we call it a day and continue next time.
Any more questions or comment?
Interested in purely CFT moduli space.
Purely CFT moduli space.
We don't assume the n equals 0, 1 and only consider CFT, so not QFT. Is it possible to say something about the CFT moduli? So
then you will most likely contain a lot of discrete set of points, right? So while we are filling this in to a more general class of theory, you see that only by doing this, you can get some interesting structure like this infinity spectrum that we get in the end. So for CFTs, I would not know any good tools like this to make strong statement about the space of theory. So, right. So one can ask this question for other class of theories, like in higher dimensions, whether there is any statement. Also, I don't know the answer to that. So I think somehow for this particular dimension, this particular amount of supersymmetry, we are having some miracle going on. So we better use it for something good.
So in this initial case that you had with this full CFTs, I was wondering how much of the continuous part of the moduli space comes from the left movers and right movers to vary, or is there some continuous sort of families of coupling left and right movers? I mean, I could imagine that maybe there's a discrete set of left and right movers, but there's a continuous family of.
Yeah, so we're asking how to get like continuous families of theories. So you know that in higher dimensions, there are often continuous families, right? For like 4D equals 4 supermules, there's an entire family parameterized by the coupling constant and theta angle tau. And then there's this famous modular, well, for S duality that map theories associated with different coupling constants. So then one can ask if one compactify those theory, whether those continuous parameters survive. So I think in general, the answer would be yes. So there should be in general moduli, or what physicists refer to as conformal manifolds in 2D. So I don't have a terribly clear or good example for this, but yeah, I think that's an interesting question.
Any other? If not, let's take a